Early 1940, and Britain's Air Force confronts a technical nightmare, claiming more aviators than enemy fire. Fighter units return from missions sharing impossible accounts. Their newest warplane, designed to dominate European skies, consistently loses dogfights against Messerschmitt Bf 109s in one devastating situation. Press your control column forward during a dive, and the Rolls-Royce power plant chokes, stutters, ceases. Between 5 and 10 seconds, you're piloting a powerless glider while a German fighter closes in. 10 seconds feels infinite when cannon fire converges at 600 miles per hour combined velocity. By late March, Fighter Command understands the mathematics. From 73 verified encounters above France and the English Channel, Spitfire aviators document power loss during inverted maneuvers in 61 cases. An 83% malfunction rate for a critical tactical movement. The distinction between achieving a firing position or becoming someone else's target. Squadron Leader Brian Lane from number 19. Squadron submits documentation reaching Air Ministry officials with immediate priority. When the German pilot initiates his dive, we pursue. Our power plant fails. He escapes. We're forced into predictable defensive patterns because our machines won't execute our commands. This emergency draws Beatrice Shilling into the narrative. She shouldn't be present at RAF Tangmere on March 23, 1940, yet the Royal Aircraft Establishment at Farnborough dispatched her to observe the defect directly. 29 years old, a motorcycle competitor holding speed achievements at Brooklands. She represents one of precious few female engineers engaged with military aviation. The establishment figures at RAE accept her presence because she earned first-class honours in mechanical sciences from the University of Manchester. Her specialisation, engine behaviour under extreme conditions, suddenly becomes Britain's most vital engineering discipline. From the dispersal building, she observes as Flight Lieutenant James Leithart demonstrates the malfunction. His Spitfire Mark I ascends to 8,000 feet, inverts, then executes a split S descent. The Merlin's steady thunder dissolves into choking gasps. Black exhaust erupts from the manifolds. Leithart recovers level flight, and after 7 torturous seconds, combustion resumes. Upon landing, he discovers Shilling already examining the aircraft, posing questions, revealing she's comprehended something the pilots experienced but couldn't verbalize. The dive angle isn't the problem, she states, reviewing her notes. It's the force vector. Whenever the aircraft encounters negative gravitational loading, fuel delivery interrupts, preventing forward stick pressure pursuit or exploiting tactical advantages. Meanwhile, the Luftwaffe operates without such constraints. Their Daimler-Benz DB-601 power plants employ direct fuel injection, a system delivering fuel into cylinders independent of aircraft orientation. Messerschmitt aviators can maneuver through any axis without missing a single combustion stroke. In the tactical warfare developing across southern England, the Germans possess complete tactical options, while the RAF fights with half its capabilities locked away. Shilling returns to Farnborough that evening, her coveralls stained with oil, facing a problem now deeply personal. The Rolls-Royce Merlin represents engineering excellence from the 1930s, yet it employs technology older than powered flight. Carburetors function on elegant simplicity. Rushing air through a constricted passage generates low pressure, drawing fuel from a reservoir into the airstream. The mixture atomizes, enters the cylinders, enabling combustion. This system operates flawlessly, provided gravity maintains fuel at the float chamber bottom, ready for delivery. Every automobile power plant in 1940 uses this principle. Every generator, every small engine, every device mixing fuel and air depends on gravity as the unseen mechanism keeping fuel properly positioned. Now invert that assumption. When a Spitfire pilot pushes into negative G-forces, everything loose in the cockpit floats upward. Charts debris the pilot's stomach contents. Inside the float chamber, fuel behaves identically. It surges away from the jets toward the chamber top, leaving pickup points drawing air. The carburetor continues attempting to draw from a momentarily empty bottom reservoir. Air rushes through without fuel. The mixture becomes dangerously lean. Combustion temperatures surge. The power plant detonates irregularly, then ceases firing. This phenomenon persists only during negative G conditions, yet in combat, 3 seconds of dead engine means 400 feet of altitude loss and a firing solution delivered to your opponent. Shilling calculates the mathematics on April 2, 1940, in her Farnborough laboratory. The Merlin's float chamber contains approximately 0.8 liters of fuel. At normal consumption rates, that provides 12 seconds of operation, meaning the float valve continuously replenishes the chamber as the carburetor feeds the power plant. Under 1G conditions, normal flight, fuel rests at the chamber floor, with roughly 1.2 pounds per square inch of hydrostatic pressure directing it toward the jets. Enter negative G forces, even momentarily, and that pressure inverts. The fuel experiences upward force, while jets continue pulling downward. Physics offers no compromise. Fuel separates from the pickup. The power plant starves, and the Spitfire transforms from weapon to liability. The German approach, fuel injection, bypasses the entire problem through mechanical force. The Daimler-Benz DB601 employs a mechanical pump pressurizing fuel to 30 psi, then precisely meters it into each cylinder through individual injectors. Gravity becomes irrelevant. Fuel lines maintain pressure regardless of aircraft attitude. A Bf-109 can fly inverted for minutes, sustain negative G until the pilot blacks out from blood pooling in the skull, and the power plant never falters. It's technologically advanced, mechanically sophisticated, and costly. Each DB601 requires precision machining of injection pumps, calibration of 9 separate injector nozzles, and maintenance demanding trained specialists. The Luftwaffe built their tactical approach around this advantage. Their aviators train to exploit it ruthlessly, push into negative G the instant a Spitfire commits to pursuit. Then observe the British power plant fail predictably. Shilling's notes from early April show her testing a theory regarding flow restriction. If the carburetor delivers excessive fuel too rapidly during transitions, and if that excess fuel creates the sloshing problem causing starvation, then perhaps limiting maximum flow rate would stabilize the float chamber. It's counterintuitive, restricting fuel delivery to solve fuel starvation, yet the physics suggest viability. The question becomes how to test it without reconstructing an entire carburetor system, and whether anyone at the Royal Aircraft Establishment will permit a junior engineer with unconventional ideas near a Merlin power plant, costing more than a home. The Royal Aircraft Establishment's formal response arrives April 9, 1940, as a 40-page technical document. Senior engineers at RAE convened multiple committees, consulted with Rolls-Royce design teams in Derby, and produced a solution involving complete carburetor assembly redesign. The proposal calls for a pressure-balanced float chamber with spring-loaded baffles, anti-slosh compartments, and a modified fuel delivery system maintaining positive pressure regardless of aircraft attitude. Estimated development timeline 8 to 11 months. Estimated unit cost £47 sterling. Estimated production disruption, complete cessation of Spitfire deliveries for 6 to 8 weeks while Rolls-Royce retools manufacturing facilities. It's May 1940. France collapses. The British Expeditionary Force faces encirclement at Dunkirk. Fighter Command operates 331 operational Spitfires, losing aircraft faster than Supermarine manufactures replacements. An 11-month development timeline isn't a solution. It's a death sentence wrapped in bureaucratic precision. Squadron commanders demand anything, any modification, any field repair, enabling their pilots to pursue German fighters without power plant failure. The establishment response creates another committee, reviewing implementation strategy for the pressure-balanced carburetor system that won't exist until 1941. Shilling reads the proposal in her Farnborough workshop and reaches a career-defining decision. She'll ignore it. Not openly. She's too intelligent to directly challenge senior engineers with 30 years' experience and extensive air ministry connections. But she'll pursue her own theory using her own methods. If successful, she'll present results making the official solution appear as it is. Over-engineered institutional thinking, prioritizing elegance over urgency. Her approach borders on insulting simplicity. If the problem involves fuel sloshing in the float chamber during negative G, and if excess fuel volume contributes to that sloshing, then restrict fuel flow entering the chamber initially. Not with springs and baffles and pressure-balanced compartments, but with a physical restriction, a washer with a precisely calculated hole drilled through its center. Install it in the fuel line feeding the carburetor. The restriction limits maximum flow rate, preventing float chamber overfilling, reducing fuel volume available for sloshing during negative G maneuvers. Less sloshing means the jet remains submerged longer. The power plant still cuts out, but for 2 seconds instead of 7. 2 seconds allows adaptation. 7 seconds guarantees death. The engineering establishment would consider this approach crude, inelegant, a plumber's remedy to an aerospace problem, precisely why Shilling doesn't request permission. She requisitions a brass disc from the RA machine shop on May 4th, 1940. The requisition form lists it as test material for fuel flow analysis. She takes it to her personal workshop, a shed behind her Farnborough flat where she rebuilds motorcycle power plants, and spends an evening with drill bits and calipers. The mathematics suggest a 0.6-inch diameter orifice for a Merlin III power plant at combat power settings. Too small starves the power plant at full throttle. Too large fails to solve the negative G problem. She drills 6 test washers at different diameters, 0.55, 0.57, 0.60, 0.63, 0.65 and 0.68 inches. By May 7th, she possesses a collection of brass discs resembling oversized coins, with holes punched through their centers. Each costs approximately 3 pence in materials. Each installs in 15 minutes by any mechanic with a wrench. Each might solve a problem costing fighter command its tactical advantage in the battle determining whether Britain survives the summer. Now she needs someone willing to let her install one onto a Merlin power plant and test what happens when you push the stick forward. Geoffrey de Havilland Jr. is the test aviator providing Shilling her opportunity. He's chief test pilot at the Airborne Forces Experimental Establishment, son of the legendary aircraft designer, someone with sufficient institutional authority to authorize unofficial modifications without immediately triggering Air Ministry inquiries. On May 14, 1940, Shilling arrives at the Hatfield Aerodrome with her brass washers wrapped in a leather tool roll. De Havilland already heard rumors about the female engineer who disassembles motorcycle power plants recreationally and who's been posing uncomfortable questions about why the RA's official carburetor solution won't be ready until spring 1941. The test aircraft is a Spitfire Mark 1. Serial number K9795, pulled from a production batch destined for 54 Squadron. Shilling and a ground crew mechanic named Albert Foley install the 0.60-inch washer in 22 minutes. It sits in the fuel line between the engine-driven pump and carburetor inlet, a brass disc slightly thicker than a shilling coin, which is where the modification eventually receives its unofficial name. The washer requires no carburetor modification itself, doesn't alter the float chamber, doesn't touch any complex metering systems Rolls-Royce engineers perfected over years. It simply sits in the fuel line. Creating a permanent restriction flow must pass through. De Havilland takes K9795 airborne at 11:30 a.m. The test protocol is straightforward. Climb to 10,000 feet, invert, push into negative G, and maintain it as long as the power plant continues running. Standard procedure expects the Merlin to cut out within 3 to 4 seconds. Shilling stands on the tarmac with a stopwatch and binoculars. The Spitfire climbs through broken cloud, levels out, inverts. From the ground, she hears the Merlin's tone change as de Havilland pushes forward. The power plant coughs once, a momentary hesitation, then continues running. 4 seconds, 5. At 8 seconds, de Havilland rolls upright and the power plant smooths immediately. He makes 3 additional passes, each time maintaining -G for progressively longer periods. The longest run achieves 11 seconds before he breaks off, not because the power plant quit, but because maintaining inverted -G, that long places enormous strain on airframe and pilot. He lands 28 minutes after takeoff and taxis to where Shilling and Foley wait. Before the propeller stops spinning, de Havilland climbs from the cockpit wearing a grin that tells the story. It still hesitates, he reports, but it doesn't cut. Maintain -G through a complete split S, and the Merlin stayed alive throughout. Rough, unhappy about it, but it didn't quit. Shilling asks about performance at full throttle, whether the restriction starves the power plant during normal combat power settings. De Havilland shakes his head. Maximum velocity unchanged. Climb rate actually feels slightly improved, probably because the mixture runs leaner and more efficiently. They test all 6 washer diameters over the following 3 days. The 0.55-inch version restricts fuel too severely. The power plant loses power above 20,000 feet, where air is thin and mixture calibration becomes critical. The 0.68-inch washer doesn't adequately solve the -G problem. The 0.60-inch diameter proves optimal, a Goldilocks solution restricting fuel just enough to prevent float chamber flooding without starving the power plant during normal operation. By May 17th, Shilling has her answer, a brass disc costing 3 pence, installable by any mechanic in 15 minutes. Solves 80% of the carburetor problem that Ray's official committee expects to fix in 11 months with a £47 redesign. Now comes the test that matters: combat performance. On May 20th, Shilling brings her data to squadron leader Brian Lane at RAF Duxford. He's skeptical. 9 years of RAF service taught him that engineering solutions promising easy fixes usually create new problems. Yet he's also desperate enough to attempt anything. Lane authorizes installation of Shilling's washers on 6 Spitfires from 19 squadrons' operational aircraft. The trial will occur in combat where -G maneuvers aren't controlled test protocols, but life or death decisions made at 300 miles per hour, with tracer rounds stitching the air around your canopy. The problem with revolutionary concepts is they threaten people who built careers on conventional wisdom. When Shilling's modification reaches the Air Ministry in late May 1940, the institutional response ranges from skepticism to outright hostility. Senior engineers at the Royal Aircraft Establishment argue that restricting fuel flow is mechanically crude, fails to address the root cause of carburetor starvation, and installing unauthorized modifications on operational fighters violates every protocol governing aircraft certification. When memo dated May 28th from an RAE department, head, whose name is carefully redacted in declassified files, refers to Shilling's washer as a plumber's bodge that may temporarily mask symptoms while creating catastrophic failure modes we haven't yet identified. The phrase Miss Shilling's orifice emerges during this period, and it's not intended as a compliment. RAF mechanics adopt it first, half mocking the notion that a problem requiring Rolls-Royce's best engineers can be solved by a woman with a drill press. The double entendre isn't subtle. It's 1940. Britain fights for survival, and institutional misogyny still finds time to express itself through innuendo. Shilling, to her credit, ignores the commentary entirely. She's too busy installing washers on every Spitfire that Squadron Leader Lane can authorize. And Lane is too busy keeping his pilots alive to care what the engineering establishment thinks of field modifications. The first combat test occurs on June 3rd, 1940, above Dunkirk. Flight Lieutenant James Coward, flying a modified Spitfire, engages a Bf-109E at 8,000 feet. The Messerschmitt pilot executes his standard escape maneuver, rolling inverted and pushing into a split-S dive. Coward follows, stick forward, expecting his Merlin to cough and die. It hesitates for perhaps a second, runs rough, then catches and holds. He stays on the 109's tail through the entire dive, closes to 200 yards, and fires a 3-second burst, tearing through the German fighter's left wing route. The Messerschmitt spins into the channel. Coward returns to Duxford and files a report reading, "Engine modification performs as advertised. Maintained pursuit through negative G maneuver that would previously have forced break-off. Recommend immediate installation across squadron." By mid-June, word spreads through fighter command like fire through dry timber. Pilots communicate, and what they're saying is that 19 squadron Spitfires can suddenly accomplish things impossible 3 weeks ago. Squadron commanders start calling Farnborough directly, bypassing official channels, demanding to know how they can acquire these washers for their aircraft. The array establishment digs in, insisting on comprehensive testing protocols, failure mode analysis, and certification procedures requiring months. Air Chief Marshal Hugh Dowding, commanding Fighter Command, cuts through the bureaucracy with a directive dated June 22nd, install Shilling's modification on all operational Spitfires immediately. Testing protocols can follow later. Right now, pilots need every advantage they can get. Production and installation become the bottleneck. Manufacturing brass washers to 0.60-inch precision isn't technically difficult, but Britain's machine shops already run 3 shifts, producing everything from bomb fuses to gun barrels. Shilling personally supervises production of the first batch, 5,000 washers manufactured by a Birmingham metalworks that normally makes plumbing fixtures. The irony of producing an aerospace modification in a plumbing factory isn't lost on anyone. Installation teams move from airfield to airfield, modifying aircraft between combat sorties. A Spitfire lands, gets rearmed and refueled, and while the pilot is in the dispersal hut drinking tea and completing combat reports, a mechanic is under the cowling, installing a 3-pence brass disc that might save that pilot's life on the next sortie. By August 1st, 1940, approximately 70% of operational Spitfires carry the modification. Combat reports from the intensifying air battles show measurable improvement. Pilots pursue more aggressively, staying engaged through maneuvers that would previously have forced disengagement. The negative G power plant cut still happens, but it's become a momentary hesitation rather than a mission-ending failure. More importantly, RAF pilots learn they can trust their aircraft to follow their instincts. That psychological shift matters as much as the mechanical fix. A pilot who knows his power plant will quit if he pushes forward is a pilot who second-guesses every tactical decision. A pilot who knows his power plant will hesitate, but hold is a pilot who fights without internal doubt, eating away at reaction time. The proof arrives in blood and wreckage scattered across the channel. On August 11th, 1940, the day the Luftwaffe designates as Adlertag, Eagle Day, the beginning of their concerted campaign to destroy the RAF, the tactical equation has shifted in ways German intelligence hasn't detected. Oberleutnant Franz Vonera, an experienced Bf-109 pilot with 13 confirmed kills, engages a Spitfire from 72 Squadron over Dover at 12,000 feet. He executes the maneuver that has worked flawlessly for 4 months, inverted roll into a negative G dive, forcing the British pilot to either break off or follow into power plant failure. The Spitfire follows. Vonera expects to see the telltale black smoke of a Merlin power plant cutting out. Instead, the British fighter stays locked to his tail, closing the distance. Vonera pulls into a climbing turn, but he's already defensive, reacting instead of dictating. the Spitfire pilot, Pilot Officer Ronald Hamlin, fires a 4-second burst at 150 yards. Cannon shells rip through Venera's cockpit canopy and power plant cowling. He belly lands in a Kent pasture and becomes a prisoner of war. Venera will eventually escape British custody and make it back to Germany, where he files detailed reports about the engagement. Luftwaffe intelligence initially dismisses his claims that Spitfires can now follow through negative G maneuvers. The Merlin carburetor problem is documented fact, verified through interrogations of RAF prisoners and technical assessment of captured aircraft. What the Germans don't know is that those assessments are based on Spitfires captured in May and June, before Shilling's modification reached operational squadrons. By August, the tactical reality has changed, but the Luftwaffe is still flying against assumptions 2 months out of date. The numbers tell the story. Between May 1st and July 31st, Fighter Command records 147 engagements where Spitfire pilots reported power plant failures during negative G combat maneuvers. Between August 1st and October 31st, the height of the Battle of Britain, that number drops to 39. The modification doesn't eliminate the problem entirely, but it reduces failure rates by 73%. More significantly, the duration of power plant cuts drops from an average of 5.8 seconds to 1.4 seconds. In the split-second world of aerial combat, that 4.4-second difference is the gap between getting your shot or getting shot. Specific engagements demonstrate the tactical transformation. On August 24th, Pilot Officer Eric Mars of 152 Squadron engages 3 Bf-109s over Manston at 15,000 feet. He's outnumbered, defensive, looking for an escape route. One of the Messerschmitts dives on him from above. Standard doctrine would be to roll away and dive with positive G, accepting the separation and hoping to outrun the pursuit. Instead, Mars rolls inverted and pushes forward into the dive directly toward the German fighter. The Merlin coughs once, briefly, then holds. The Bf-109 pilot, expecting the Spitfire's power plant to fail, doesn't react until Mars is firing head-on at convergent closing velocity. The German breaks off, Mars reverses, and suddenly he's on the tail of one of the other 109s. He scores hits on 2 aircraft and returns to base, having survived an engagement that should have ended with him spiraling into the September 15, 1940, the day that will later be commemorated as Battle of Britain Day, sees 56 confirmed Luftwaffe aircraft destroyed over southern England. Flight records indicate that in at least 19 of those engagements, Spitfire pilots successfully pursued through negative G maneuvers that would have forced disengagement prior to the carburetor modification. That's 19 instances where Miss Shilling's orifice directly contributed to a German aircraft being destroyed rather than escaping. Extrapolate across the entire 3-month period of intense combat, and the modification may have influenced the outcome of 150 to 200 engagements. Squadron leader Lane, who authorized the first combat trials back in May, writes a letter to Shilling in late September. It's brief, typed on official RAF stationery, with formatting suggesting Lane composed it himself rather than delegating to a clerk. Your modification has kept pilots alive and aircraft operational. The mathematics of survival don't measure elegance, they measure effectiveness. Thank you for understanding the difference. The letter arrives at Farnborough on September 28th. Shilling files it in her desk drawer without showing it to the senior engineers who spent the summer arguing that her solution was mechanically inadequate. The institutional lesson takes years to penetrate the engineering establishment, and even then it arrives wrapped in reluctance. Miss Shilling's orifice works, but it offends the sensibilities of engineers trained to believe that proper solutions require comprehensive analysis, systematic redesign, and elegance in execution. A brass washer with a hole drilled through it possesses none of these qualities. It's a restriction, a compromise, a band-aid addressing symptoms rather than root causes. That it saves lives and wins battles doesn't make it beautiful. And for a certain type of engineer, beauty matters almost as much as function. Rolls-Royce eventually develops the proper solution everyone knew was coming. By March 1941, they introduced the Bendix-Stromberg pressure carburetor, a sophisticated system using fuel pumps and pressure regulation to maintain consistent mixture regardless of aircraft attitude. It's everything the RAE committees wanted. Engineered, tested, certified, and elegant. It also costs £43 per unit, requires specialized installation, and needs recalibration every 100 flight hours. Shilling's washer costs 3 pence, installs in 15 minutes, and requires 0 maintenance. Both solutions work. One is objectively superior from an engineering purity standpoint. The other won the Battle of Britain. The contrast exposes a philosophical divide in how engineers approach problems under time pressure. The establishment method, comprehensive analysis leading to optimal solutions, works beautifully when you have the luxury of development time. It produces aircraft like the later Merlin variants, with 2-stage superchargers and sophisticated fuel management systems. Power plants representing the pinnacle of piston aviation technology. But in May 1940, with France collapsing and fighter command hemorrhaging pilots, the establishment method would have delivered its solution in April 1941, 9 months too late to matter. Shilling's approach: identify the minimum viable intervention addressing the critical failure mode, delivered results in 3 weeks. This isn't an argument against engineering rigor or comprehensive design. The Bendix-Stromberg carburetor is genuinely superior to a restricted float carburetor with a brass washer in the fuel line. What Shilling's modification demonstrates is that superior and adequate occupy different positions on the timeline of urgent. Fighter command didn't need the perfect carburetor in 1941. They needed a working carburetor in June 1940. Shilling gave them adequate, and adequate was enough to keep Britain fighting until superior could arrive. The broader aerospace industry slowly absorbs this lesson through the 1940s and 1950s. Lockheed Skunk Works, formed in 1943, operates on principles that would have been familiar to Shilling: fast iteration, minimal bureaucracy, solutions prioritizing function over elegance. Kelly Johnson, the legendary Skunk Works director, keeps a brass disc on his desk throughout his career, a replica of Miss Shilling's orifice that a British colleague gave him in 1946. When engineers propose elaborate solutions to urgent problems, Johnson taps the disc and asks whether they're designing for perfection or designing for delivery. The question usually clarifies thinking remarkably fast. Modern Formula One racing carries forward the same philosophy. Teams spend hundreds of millions developing sophisticated power plants with pneumatic valve systems, hybrid power units, and fuel injection that can meter delivery to microsecond precision. They also carry rolls of aluminum tape, cable ties, and various quick-fix solutions that would horrify aerospace engineers, but that keep million-pound racing cars operational during 2-hour Grand Prix events. The F1 engineers understand what Shilling understood in 1940. Complexity is impressive, but reliability under stress is what actually wins. The irony is that Shilling's modification remains in some ways more robust than its sophisticated replacement. The Bendix-Stromberg carburetor has multiple failure modes: pump failure, pressure regulator malfunction, diaphragm rupture, accelerator pump sticking. Miss Shilling's orifice has exactly one failure mode: the brass washer physically breaking, which requires stress levels that would have already destroyed the rest of the power plant. Simplicity creates its own form of reliability. A system with fewer moving parts has fewer things that can break. This seems obvious, yet engineering culture consistently forgets it. Seduced by the intellectual satisfaction of solving problems with maximum sophistication rather than minimum necessary complexity, Air Chief Marshal Dowding In his post-war memoirs published in 1946, dedicates 3 paragraphs to the carburetor modification. He writes, "Miss Shilling's contribution exemplified the kind of practical thinking that kept Fighter Command operational during our most desperate period. History will remember the Spitfire's grace and the Hurricane's ruggedness. Those of us who were there will remember the 3-pence brass washer that let both aircraft fight as their designers intended. It's one of the few instances where a senior commander explicitly credits an engineer by name for tactical advantage in combat. Beatrice Shilling returns to peacetime obscurity with the same quiet competence that characterized her wartime contribution. In 1948, she's awarded an OBE, Order of the British Empire, for her services to aircraft engineering. The citation is brief, mentioning contributions to power plant performance under combat conditions without specifying the brass washer that influenced hundreds of aerial engagements. She attends the investiture ceremony at Buckingham Palace, receives her medal from King George VI, and returns to Farnborough the next day to continue work on jet power plant development. The ceremony receives 2 paragraphs in the Times, buried on page 11 between notices about agricultural subsidies and railway timetable changes. Post-war, Shilling shifts her focus to jet propulsion and supersonic flight research. She works on the de Havilland Ghost Power Plant, contributes to early studies of afterburner technology, and helps develop test protocols for measuring jet power plant performance at transonic velocities. It's important classified work that pushes Britain's aviation industry toward the jet age. It's also work that history largely forgets, overshadowed by more prominent engineers and the institutional amnesia that settles over technical contributions once the immediate crisis passes. By 1950, new RAF pilots training on Spitfires don't know why there's a brass washer in their fuel line, only that regulation requires it to be there. The modification has become invisible infrastructure, taken for granted. She retires from the Royal Aircraft Establishment in 1969 after 39 years of service. Her personnel file, declassified in 2003, contains performance reviews consistently, rating her as technically proficient and reliable, the kind of faint praise that defines institutional mediocrity rather than revolutionary contribution. One supervisor notes in a 1952 review that Miss Shilling sometimes displays impatience with procedural requirements, which translates as, she still thinks 3-pence brass washers are better answers than 11-month development programs. The RA hierarchy never quite forgives her for being correct in ways that made them look foolish. Motorcycle racing continues through the 1950s. She competes at Brooklands until the circuit closes, then shifts to trials riding and hill climbs. In 1965, at age 54, she sets a speed record for women over 50 on a Norton Dominator at the Silverstone circuit, 118 miles per hour on a machine. She rebuilt herself in her garage. The motorcycling press covers it with more enthusiasm than aviation journals ever showed for her carburetor work. There's something about a grandmother in a leather suit outrunning men half her age that captures public imagination more vividly than fuel flow dynamics. Beatrice Shilling dies on November 18, 1990, at age 79. The obituaries in major newspapers are brief. The Times gives her 4 paragraphs mentioning the OBE and describing her as an engineer who contributed to aircraft development during the Second World War. The Daily Telegraph manages 6 paragraphs and includes a photograph from 1940 showing her standing next to a Spitfire, though the caption misidentifies the aircraft squadron. Neither obituary mentions Miss Shilling's orifice by name, perhaps because editors in 1990 still consider the double entendre too crude for print, or perhaps because by 1990 nobody remembers what the phrase meant. Recognition begins arriving after she's no longer alive to receive it. In 2013, the Royal Academy of Engineering includes her in their Engineering Heritage series with a blue plaque mounted at the site of the former RAE Farnborough building where she worked. In 2017, The Brooklands Museum opens an exhibition on women in motorsport and engineering that features her prominently. The Imperial War Museum adds her story to their Battle of Britain displays in 2020. 80 years after the modification she developed changed the tactical calculus over southern England. Modern engineering students occasionally learn about her in case studies about rapid prototyping and minimum viable solutions, though usually without context about the misogyny that shaped how her contribution was received. The brass washer itself becomes a collector's item. Original examples from 1940, stamped with RAF inventory numbers, sell at aviation memorabilia auctions for hundreds of pounds. Museums display them in cases next to Merlin power plant cutaways and Spitfire propeller blades, small brass discs with holes drilled through their centers, objects that look unremarkable until you understand what they accomplished. Each one represents a choice, the choice to deliver adequate immediately rather than perfect eventually, to ignore institutional hierarchy in favor of practical results, to understand that elegance matters less than effectiveness. When people are dying because their power plants quit at the worst possible moment, the final irony is that Beatrice Shilling would probably find the posthumous recognition bemusing. She solved a problem using the tools and knowledge available, which is what engineers do. That it worked doesn't make it heroic, it makes it functional. That it saved lives doesn't make her special, it makes the problem worth solving. She spent her career believing that engineering was about making things work, not about receiving credit for making things work. The brass washer proved her right. 3 pence worth of metal and an afternoon with a drill press turned out to be exactly enough.